For the midterm, yeah, for the midterm. No, for the second one there isn't. The review is already open. Anion gap. So anion and cation. So anion is anything that's negative charge. A cation is anything that is positive charge. What's that? Anion is anything with a negative charge. So in this case, chloride has a negative charge. It would be an anion. Anything with a positive charge is called a cation. That just means it has a positive charge. Yeah. So we're just measuring the difference between the charges, positive and negative. So add up all your positive charges, add up all your negative charges, and find the difference in charge. Right. So here we got sodium, which is positive, right? And then we got chloride, which is negative, and then we got this bicarbonate, which is negative, right? So we have 140 positive stuff, 105 negative stuff, 22 negative stuff. Overall, what is my charge overall? 140 minus 105 minus 22. 13, there you go, that's it. So for B, what would be your anion gap? How much negative charges are you short by? What'd you get for B? 25, all right. So what is an MEQ? What does MEQ stand for? Yep, so MEQ stands for milliequivalence. And what an equivalence is measuring is charge. So since we're talking about ions, we got to measure charge. And we'll talk about pH shortly, which measures positive and negative charges. MEQs, milliequivalence. Gas density. So one thing to know is the ideal gas law. For 1 mole of gas, and this is at STP, standard temperature and pressure, the volume that it will occupy is 22.4 liters. First of all, Mr. Dang, what the heck is a mole? What's a mole? This thing? Close, close. A mole is a number like a dozen. If I say a dozen, what does that mean to you guys? 12, yeah. If I say a gross, what does that mean to you guys? You don't know what a gross is? What's 12 times 12? 144, that's a gross. That's a dozen is a gross. What's a great gross? A dozens, right? So once you put a name to a number, it changes the meaning. The value of a mole is 6.023 times 10 to the 23rd. So instead of writing this number with a bunch of zeros all the time, we're just going to say mole, right? And how that helps us is 1 gram, right? The atomic mass unit of hydrogen is 1. So if I measured out 1 gram of hydrogen, right, I know I have 6.023 times 10 to the 23rd molecules. If it's hydrogen gas, H2, if I measure out 2 grams of hydrogen gas, I know that I will have 6.023 times 10 to the 23rd molecules of hydrogen. So the atomic mass unit tells you how much you need to measure in order to get 1 mole. Exactly 1 mole of molecules.
Is that 2 now or 1?
It's 2 grams because I said hydrogen gas.
Okay.
Yeah. So the first example was just hydrogen. It'd be just 1 gram because that's the atomic mass. But in our atmosphere, hydrogen is H2. So if you measured out 2 grams of hydrogen gas, you'll have exactly 1 mole. So let's find the weight. So it's a weighted average for gas density. So all of these are just singular gas mixture. So this is just one gas. So you only have to do the front part, just the first gas. So you're going to add in the molecular weight of the molecule, the gas, times the percentage of the mixture. So for these, it's 100% carbon dioxide for A. B, 100% oxygen, nitrogen, and I guess that's ammonia gas. So C equals how many grams per mole? You gotta look at your periodic chart. Oxygen equals how many grams per mole? Carbon, what is it? 12 point, what's the mass? 12.0111. Okay, we'll just use 12. What's oxygen? What's the mass of oxygen? 15.99? What was it? 15.99. Oh yeah, we can just use 16. So we'll round to the nearest 0.1 gram. All right, so how many carbons do we have? Just 1, right? Just 1 carbon. So overall, that's 12. How many oxygens do we have? 2. So we got to multiply this number by 2. So that's going to be 32. So CO2 weighs how much per mole? If there's 1 carbon and 2 oxygens, I need to measure out how many grams of CO2 to get 1 mole. 44. Right. So go to your CO2 tank, measure out 44 grams, right? And if you release it at STP, what volume will it occupy? 22.4. So 1 mole at STP gives you how many molecules. So if you have 22.4 liters, I know the number of molecules. Correlates. All right, let's do oxygen. All right, oh, we got to solve this first. How many grams per mole? So we figured out that it's 44 grams per mole. Figure out oxygen. How many grams per mole? O2. So oxygen is 16, but there's 2 of them, so that's just 32. What's nitrogen? What's the atomic mass of nitrogen? So nitrogen is 14 point something. You gotta look at your table. I don't have the list on me. Okay, so straight up 14, and there's 2 of them, so that's going to be 28. All right, N is 14. H's are just 1 each, so I know that's 3, so that's 17. So if you measure out those amounts of grams of substance, you know exactly how many molecules you have. So that is Avogadro's number. 6.023 times 6.022. 6.022. All right, now let's find the densities. So since we know the atomic mass, CO2 was what, 44? Right, grams per mole. What was oxygen? Previous slide. 32. All right, so I'm asking you guys because you got to know where these numbers come from. All right, now all we do is plug and chug. So let's do A right here. So the mass of the first item is 44. And we got to multiply by 10%. So I'll multiply by the decimal. You guys know how to change a percentage into a decimal, right? That's the first lesson. Fraction, decimal, percentage. So change it to a decimal will make your life a lot easier. Add that to the mass of oxygen, which is 32, and times the weighted average, which is 0.9. Do everything above the fraction bar before you divide by 22.4.
Where do you get the 0.9 again?
90%. So I took the 90% here and I divided it by 100 to get my decimal, 0.9. That way I don't have to worry about percent signs. Right? So all I did was a fraction decimal percentage conversion, which you guys know how to do. If not, refer back to less than 1.1. All right, what do you guys get as the density, grams per liter?
So that one would be 33.2.
What?
Then divided by 22.4.
What? All right, somebody punch this in for me. What's 32 times 0.9?
28.8.
28.8. So you got, what is it, 28, 33.2 over 22.4, and then you simplified it to 1.4. There you go, grams per liter. That's it. Super easy, as long as there's only a couple mixtures. So let's do B. So helium, what is the atomic mass of helium? Not the number, atomic mass. Mass. Gross molecular weight. So what's the atomic mass? Look at your periodic table. There's 80 guys in here. What's the mass of helium? Upper right, top one. Oh my God, you can't. Oh my God, you guys cannot find. All right, 4. And then oxygen's 32. So let's plug that in. We got 4 times 0.7 plus 32 times 0.3. Sorry, I should put 0.7 over 22.4. And then all you do is simplify it from that point. All right, so we got 2.8 plus, what is that, 9.6 over 22.4. Come on, guys. You got calculators. You got to punch it in quicker. So, what's the density? How many grams per liter? I got 0.
0.5.
About 0.5. All right, let's do C. Now we have 3 items, but nothing changes. Helium is 4. Nitrogen we figured out. What was nitrogen in? 14? Is it 14 or 28? 14. Oxygen is 32. 14. So that's the mass or the number. All right, so do 4 times 5%, 0.05, plus nitrogen, which is 14 times 75%, 0.75, plus oxygen, which is 32 times 0.2%. Do everything in your numerator before you divide by the ideal gas law. 1 mole occupies 22.4 liters. I got 0.2 plus, what is that, 7, 8, 9, 10.5, I think, plus 6.4 over 22.4. guys get?
7.
About 0.7. Okay, not too bad. So I'll leave D for you guys. So make sure you do that, show your work. So the submissions from last week, a few of you guys didn't show all your work. So go back and do D before you submit. All right, let's go on. Concentrations. We can measure concentrations a couple ways. So there's percent concentration. There is by volume, right? So there is, I think alcohol is sold by volume. So it's 40% by volume. Right, so that's different. Right, that's one way to measure it. You can do it out of percentage, you can do it by volume, you can do it by weight. For chemistry, we're going to use molarity, and that's going to use moles. And it's easy, just take the number of moles over liters, and the symbol for molarity is capital M. So anytime you see a capital M, you know that that is moles per liter. Right? We know to calculate moles in many ways. We know moles by grams, we know by the number of molecules, and we also know by volume, 22.4 liters, right? So all three is going to mean the same thing. So at ideal gas, it's going to occupy that much volume. 1 mole is going to have 6.022 molecules. And if I look up the atomic mass, then I know how many grams to get a mole. All right, so we have 25 grams. First we got to figure out moles. So 1 mole of sodium chloride weighs how much? So what's the atomic mass of sodium? Na. 20 what? 22 point nothing? 22.98. Let's use 23. And then what is the atomic mass of chloride? 35. Let's do 35.4. It was 35.43. 0.45? Let's use 35.5. Alright, that's better. Alright, so that's how much 1 mole weighs. But how many grams do we have? We only have 25 grams. Right? And the atomic mass is, well, we got to add that together. 23 plus 35.5 is how many grams?
58.5.
58.5. So divided by 58.5 grams per mole. So how many moles do we have? 25 divided by 58.5. 0.4. That's moles. We're not done yet. We don't want moles. We want molarity. So don't round it. Take that number and you're going to divide that by the number of liters, which is 1.5. Now we are in the correct units. Moles per liter for molarity. 0.4 divided by 1.5. Yeah, 0.26. A little better. Not too bad. All right, first you got to find the number of moles. All right, and then you just divide it by liters. Okay, potassium. How many grams per potassium atom? Okay, potassium, how many? Okay. So on the left hand side. How much? 39? 39.1. Yeah, 0.09, right? Yeah, round to the nearest 1 decimal place. So that means the atomic mass of potassium chloride.
So every time we look up for whatever, we need to just round up?
Yeah, round it to the nearest. So that means round up or down, right? So not just round up, it's round. Yeah, round is round. So potassium is 39.1 per you guys. Chloride is 35.5. So 1 mole would equal how many grams? Add them together. 74.6. 39.1.
I get confused because sometimes you're rounding up, sometimes you're not.
I'm just rounding to the nearest tenths. So sometimes you round up, sometimes you round down because you look to the right. So for 39.09, I'm rounding to this decimal place. That means I have to look to the right. Does it stay at 0 or does it go to 1? So it's not if I'm rounding up or down arbitrarily. I'm just following the rounding rules to the nearest 1 decimal place. Capiche? Comprende? You got it? Hiểu không? Có không? Nói tiếng Việt ha? Ok. Bây giờ mình nói tiếng Việt. Ok, bây giờ mình nói tiếng Việt. Đủ không nói tiếng Anh, nói tiếng Việt. Ok, bây giờ 1 liter mấy? 500 ml một mấy liter? No, we want liters. We want liters. 500 mils is how many liters? What does milli mean? 1/1000th. So that means you have half a liter. So let's do B. So we got 100 grams of potassium chloride. The molecular mass is 74.6 grams per mole, and the volume is 0.5 liters. So just do it all together. Do 100 divided by 74.6 divided by 0.5. What's the entire decimal? 2.68. Okay, sounds good. So here it doesn't tell you, but a couple decimal places will help you. C. So what is the molecular mass for sugar? Compute that real quick, everyone. We'll do this and then we'll take a break. All right, so we got 12 by 6 equals, we got 1 by 12 equals, oxygen is 16 by 6 equals, and 12, 72 grams, this is 12, 6 times 6 is 36, 6, 7, 8, 9. All right, add those all together. I got 0, 9, 10, 11, 180. Yep, carbon's 12, right? And then hydrogen is 1, oxygen is 16. Yep, 180 grams per mole. So we'll take the grams we have, 375 grams, divided by grams per mole, divided by the 5 liters, and you're done. So 375 divided by 180 divided by 5. 0.41. Okay, about 0.42. 41, 42. Okay. All right, so I'll leave D for you guys. So find the molecular mass, change the volume into liters. All right, let's go ahead and take a break. We'll come back. We'll finish this up. All right, conversions. So this is all 1, 2, 3, 4, 5 different ways of saying the same thing. Right. So 1 atmosphere. So here you are standing, and above you is a big old long column of gas that's pushing down on you. Right. So 1 atmosphere of pressure is pushing 760 millimeters of mercury, which is the same as a torr. Right? 760 torr is an atmosphere. Now, if we change that substance from mercury to water, atmospheric pressure will support a column that is 1,034 centimeters high. And if we wanted it in pounds per square inch, like you use to inflate your tires, then it's 14.7. So all around you, the atmosphere is pushing down on you at all angles, every part of your body. You don't feel it. And if you want to measure it in kilopascals, it'll be 101. So this exercise is just conversion. And if you forgot how to convert, just go back. All you need to do is multiply or divide. That's it, by the conversion factor. Your job is to figure out which factor to use, and if you multiply or divide. Torr to PSI. So one trick that you can do is use the memory key on your calculator, convert everything to ATMs, and from there all you have to do is multiply by the conversion factor. Right. So let's set it up. Torr, so there's 500 torrs, but I know that 1 atmosphere is 760 torr. So already that's my atmosphere value. Right. So I know that this is my atmosphere value. So to find PSI, all I have to do is multiply by PSI. And then to find kilopascals, all I got to do is multiply by 1.1. Times 14.7 will give me PSI. If I do the same, 500 torr over 760 torr, that changes to atmosphere. And then all I have to do is multiply by my conversion factor. So, how many PSI is 500 torrs? 500 divided by 760 times 14.7. 9.67, okay. So do the same, 500 divided by 760 times 101. 70, how many? Did you punch it in? What do you guys get for KPAs? 66? Okay. So we're guessing about 70. 66 sounds about right. So if you know how to use your memory key, all you gotta do is punch this thing once, and then you can just use it every time. All right, let's do B. So for B, we have 850 millimeters of Hg. I know that for every atmosphere, I get 760 millimeters of Hg. So that is my pressure in atoms. And to get PSI, all I got to do is multiply by 14.7 to get PSI. And then all I have to do is multiply by 1,034 to get centimeters of water. So 850 millimeters of mercury is how many atmospheres? So take 850 divided by 760. How many atmospheres is that? 1.18, right? So you already know atmosphere. All you gotta do is take that number, multiply by your PSI, 14.7. So you got 16 here. So do the same thing unless you use your memory key. So just punch it in again. 850 divided by 760 gives you atmosphere times your conversion factor, 1,034. How many centimeters do you get? 1, 2, the conversion factor for centimeters of water is 1034. 1156. So yeah, about 1200. The math I did in my head, so about 1156 sounds about right.
We don't put the decimals in here?
For this exercise, no. We should be okay. On your assignments, it'll let you know. Maybe. All right, PSI. All right, so let's divide by 14.7. That'll give you atmosphere. To get to pKa's, just multiply by the pKa value. And then to get atmosphere, well, guess what? You already solved it, so you're good to go. 50 divided by 14.7, that gives you atmosphere. 3.4. And then just multiply by 101 to get your kPa's. Oh, 343. About 343. So this is just a conversion exercise. So commit to memory these 5. All 5 equals 1 atmosphere. So when we do gas laws, you have to be in the same units for them to cancel out, for the units to cancel out. All right, let's start with the combined gas laws. And this shows you the relationship between pressure, volume, and temperature. And the best thing to do is just to look at 2 variables at a time. So the combined gas law is your initial condition. So all the 1s means your initial condition. And all the subscript 2s means your final condition. So it's very important. So all your initial conditions on one side, all your final conditions on the other side. Start with this equation. PV over T equals PV over T. Pressure times volume over temperature will equal pressure times volume over temperature. So if you change one variable, it'll change the other variables, right? So this is saying pressure and volume are going to be relational. So if you increase pressure, what happens to the volume? When you increase the pressure, the volume will go down, right? So if you decrease the pressure, the volume will go up, right? So if you put marshmallows in a vacuum, they'll expand, right? So if you put a marshmallow under pressure, it's going to shrink, right? So that's what pressure and volume does. Pressure and temperature, the relationship is the higher the temperature, the higher the pressure. So in a pressure cooker, does it cook faster or slower? Why? You can increase the temperature above boiling. That's why it cooks faster. So boiling is 212. If you use a pressure cooker, you can get that temperature up to 250, 260. Make your bomb. That guy they arrested, right? Volume and temperature. Right? Same. It has an inverse relationship. As you increase the temperature, the volume will also increase, right? Because the molecules are moving faster, it's going to increase the volume. If you reduce the temperature, the molecules are moving slower, then the volume will be smaller. So that's just the relationship with the gas laws. So temperature, you must be in Ks. You must be in Kelvins. So it's just a plug and chug, solve for the missing variable. So let's convert everything into our units that we need, right? So liters and liters are the same, so we don't have to worry about those, right? Temperatures, we got to convert to Kelvin. So let's do this. So what is 82 plus 273? That'll give us our temperature in Kelvin. What is it? 355. Okay. Torrs. We got to divide by 760. And that'll give us our atmosphere. All right, so we're in K here. That's good. We're in atmosphere here. We're in atmosphere here. Fahrenheit. So somebody Google 120 in Celsius real quick so we don't have to do the math. Nobody? All right, do the math then. Nobody? You want to use the equation? All right, let's use the equation. 120 Celsius. What is it? What is it in Celsius? 120 F to C. All right, I punched it in. Thank you. So it is 48.9. Let's add in 273. What do you get? 22.9. All right. So now we're ready to plug and chug. So P1, let's plug that in. 150 over 760. We're going to round at the end. Volume 1 is 3 liters. And the temperature T1 is 355. That all equals to P2, which is what we'll solve for. The volume of 2, which is 4 liters. And the temperature, which is 322.9. All right, everyone solve for P. Let me know what you get. So it's algebra at this point.
It's actually 321.9.
321.9? Okay, 321.9. All right, solve for P. All right, I'll put it in. So now it's just crunching numbers. Make sure you guys are able to punch this in. So I'm going to do 150 divided by 760 times 3 equals divided by 355 times 321.9 divided by 4. I got 0.13 ATMs. Algebra, solve for P. Who multiplied by the reciprocal? Nobody? So all you have to do to get P by itself is to multiply by the reciprocal. So 4 goes on the bottom, 321.9 goes here. What we do to one side, we have to do to the other side. So multiply by 321.9 over 4. And then just crunch this side, and you're done.
I have a quick question.
Mm-hmm.
Where you got the times 3 and times 4, you were adding the value, and how'd you get the times 3 and the times 4?
It's in the equation. It says pressure times volume. So P1 times V1, and then P2 times V2. So that dot goes right here. So you multiply by the volume, which is given here. All right, let's go on to the next one. So again, you got to change everything to the units that you want. All right, so 40, let's convert that into Kelvin. What'd you get for Kelvin? 4.44 plus 273 plus 273. let's round it. Let's round it 277. All right, cc's and ml's are the same, so those are good. So this one we just need to add 273. And then kPAs we need to divide by 1.1. That'll give us ATMs. All right, our units are good. Kelvin, Kelvin. We got cc, which are mLs. Those are the same. And then atmosphere and atmosphere. Now all we have to do is plug and chug. Right, so P1 is 200 divided by 101. And we're going to multiply by the volume, which is 500, over the temperature, which is 277. And that all is going to equal P2 times your volume, which is 200, over T2, which is 293. Right? So multiply by the reciprocal and don't round until the very, very end. So if you wrote down numbers intermittently, that's going to compound your errors. 200 divided by 101 times 500 divided by 277 times 293 divided by 200. So I punched everything in without writing any numbers down. I got 5.23 ATMs. So yeah, that should be right. We went from a 500 volume, squeezed it down to over half. So the pressure went from 200 or 2 atmospheres to 5. So that makes sense. All right, so this is the hardest one where you have 6 variables to deal with. The reason I do this one first because it gives you the golden equation. PV over T equals PV over T. Right? If you start with that equation, all the other gas laws will be easy. All right, so here we got Boyles Law. So PV over T, all they did was they removed the T, right? So normally we would have PV over T1 equals PV over T2, right? So this is only pressure and volume comparison. So to start, I like using this. The initial value equals the second value. Plug and chug. So let's go and do A. Torr is in torr. Liters, I'm happy. I don't have to convert the units. They'll cancel out. So all you gotta do is plug it in. 600 torrs times 3 liters equals 850 torrs times V2. So V2 equals how much? All you gotta do is divide both sides by 850. 600 times 3 divided by 850, and your volume is 2.11 liters. Right? So now that you know the combined gas laws, these fraction ones are a lot easier. B, we're going to do it the same exact way. So mLs and liters, so let's change this guy to liters, 0.95. Let's change this guy to atmosphere by dividing by 14.7. All right, now all we have to do is plug and chug. P1, 53 over 14.7. Volume of 1 is 0.95 liters. Our atmosphere is 3, and we need to find V2. So all we have to do is divide both sides by 3. So do your rounding at the end. 53 divided by 14.7 times 0.95 divided by 3. And I got a volume of about 1.14 liters. So we went from 35 divided by 14.7 We went from 3.6 ATMs to 3. So yeah, that's about right. The volume should expand. Boyles Law, pressure and volume. Chars Law, PV over T equals PV over T. So here all they did was remove the pressure consideration. So PV over T equals PV over T. So they took away pressure. So you can just do initial volume over temperature equals final volume over final temperature. These are just rearrangements. This is the same equation, they just rearrange it. This is the same equation, they just rearranged it. So you can use any one you want. Let's go ahead and use this one. Same format we've been using. T1 V2, T2 V1. So just be careful. A little bit different from Boyles Law. Plug and chug. So temperatures, what values do we have to be in? Kelvin. So this becomes 323. Liters are good. So let's do the Fahrenheit. So 85. Celsius is 29.44 plus 273. About 302.4. All right, now we're ready to plug it in. T1, 323. V2 is what we're looking for. Thank you. T2 is 302.4 and V1 was 5. So all we do is divide both sides by 323. V2 equals 302.4 times 5 divided by 323. So a little reduction in volume because of the temperature went down. So the volume went down. So very good. Makes sense. B, let's change that one. That's 0.8 liters. Celsius plus 273. So this becomes 333. 100 degrees Fahrenheit. Let's see what that becomes. 100 is about 37.8 plus 273. So Kelvin, liters. Now let's plug and jug. T1, 310.8. V2 is what we're looking for. Equals T2, 333 times V1, which is 0.8. Divide both sides by 310.8. So the temperature went down a little, went up a little, so 0.85, 0.86 liters, 857. Not too bad for the plug and chug, but you have to convert into like units for them to cancel out.
Is that a 3 or 5?
It's a 5. 5, so round up to 6. Another variation, and this is the last one of the combined gas laws. This time they eliminated volume. So just use T1, P2, T2, P1. And again, everything needs to be in the appropriate units. Torr divided by 760 will give me ATM. And let's change that Fahrenheit number. 150F. $65.6 plus 273. .6. So we're in Kelvin, we're in Kelvin, we're in atmosphere, we're in atmosphere. Plug and chug. T1. 6, yeah. So T1, 353. P2 is what we're looking for. That is equal to T2, 338.6 times pressure 1, which is 250 over 760. Divide both sides by 353. P2 equals, all right, let's punch this guy in. 250 divided by 760 times 338.6 divided by 353. And I got a pressure of 0.315, so about 0.32 atmosphere. 250 divided by 760. All right, B, same thing. Atmosphere, we'll need to divide by 14.7 to be an atmosphere. Plus 273 here for Kelvin. That becomes 313. Let's do 105. 105 degrees is 40.6. We'll add 273 to that. $313.6. Huh. So the temperature is about the same. Yeah, is that the exact temperature? That's the same. 100 degrees Fahrenheit, 40 Celsius.
0.6 degrees.
Yeah, so guess what? This is gonna be whatever this is. A bunch of the stuff's just gonna cancel out. So all we have to do is do 68 divided by 14.7. Yeah, 4.63. So we didn't even have to do the other stuff. This guy just canceled out that guy. So we just had to solve. P1 is going to be the same as P2 pretty much. Not much of a change. Alright, one more gas law to use, and it's going to be the ideal gas law. Alright, so before we can use the ideal gas law, you got to understand that mole again. Alright, so here it comes up again. So you guys know that 1 mole is 6.02 times 10 to the 23rd molecules. And at STP, 1 mole of gas will occupy 22.4 liters of space. N is the number of moles. K is a constant. And you have to pick the correct one based on your units. And V, your volume. Right? So all this is saying is, well, mole of gas can occupy that volume. All right, so if I have 200 grams of oxygen, how many moles do I have? Well, an oxygen, O2, how many grams per mole? What's oxygen? What's one oxygen? You gotta look at your periodic table. We already did this earlier, 16. So if you got 2 of them, that's gonna be 32 grams per mole. All right. But how many moles do you have? I have 200 grams of oxygen. I gotta divide that by my molecular weight, which is 32 grams per mole. That gives me moles, right? So how many moles do I have? 200 divided by 32. How many moles do you have? 6.25 moles. So what do you know about every mole? How much volume does every mole occupy? 22.4. There you go. So take the number of moles, 6.25, multiply by 140 liters? Yeah, about right. So about 6 moles, 6 times that, 140 liters, yeah. So your strategy is first you got to figure out how many moles. So we got this many molecules. How many moles is that? What do? Take that number. So this is A. For B to find moles, I got 8.3 times 10 to the 24 molecules divided by 6.02 times 10 to the 23rd. Right, you can write out all the zeros if you want, or you can subtract exponents. Right. So take 8.3 divided by 6.02 times, this would be 10 to the 1, right? So 24 minus 23 would just be 1, so that would be 10. So how many moles do we have? 8.3 times 6.02 times 10. How many moles is that? 13.78 moles. All right. And how many moles, how many liters do we get per mole? So just take that number and multiply by 22.4. All right. So all I got to do is divide. You got that many molecules, divide by the number of molecules per mole. This will give you moles, and then all you have to do is multiply by the liters. 308? Okay, so about 308. Moles. First you got to figure out moles. All right, I got 800 liters of helium. How many moles is that? How many liters per mole? It's just a conversion factor, guys. So if you're changing, so these are your conversion factors. Use them just like we've been doing. So 22.4 liters is a mole, and I got 800 of it. So how many moles of helium do we have?
28.
How much?
35.
35? It's 800 divided by 22.5. So you don't even need to know what the stuff is. We're assuming it's an ideal gas, so all you gotta know is the volume. Nitrogen. What's the atomic mass for nitrogen gas? N2. So nitrogen gas is 28. 28 grams per mole. Right? So we got 65 grams, 28 grams per mole, and all you do is multiply by the volume, 22.4 liters. 65 divided by 28 times 22.4. Are you sure? You sure?
65.
Divided by 28. I only got like 40, 50, what do you get?
22 times 4 is 52.
52.
Yeah, that's what he said.
Oh, okay. 52.
52.
Yeah. All right, so that is conversion. This is just a conversion. So I gave you a couple more conversion factors. We used them earlier as well. All right, lastly for today is the ideal gas law. The ideal gas law is given to you as pressure times volume equals the number of moles times your constant R times temperature. Now, your constant value will depend on the units you're using. So if you're using atoms and mLs, then you're going to use an R value of 82.1. If you're using pascals and meters cube, then you're going to use some weird number. I don't like this one. Right? Easier for me is liters and atoms. Meters cube, what the heck is a meter cube? Right? It's going to make you do conversion. So let's use this guy. So all we have to do is convert into similar units. So we have to be in atoms, atmospheres, we're good there. Do we want to be in liters? No, we need to be in what units? mLs. So just convert that to mLs because you got to be in your correct units. And then Celsius, do we want Celsius? Nada, never, right? 343. Now we're okay to plug and chug as long as we are using the units of our constant. So let's plug and chug. So P is 1.5 ATMs. Volume is 4,000. N is what we're solving for. Our R value is 82.1. And our temperature is 343. So all we do is solve for N. So we're going to divide both sides by 82.1 times 343. So how many moles do we have in this ideal gas setup? 1.5 times 4,000 divided by 82.1 divided by 343. 1.5 divided by 4,000. Sorry, 1.5 times 4,000 divided by 82.1 divided by 343. That gives you about 0.21 moles. So these problems, not too bad. You just got to make sure you're in the correct units. So conversion. Practice your conversions. PSI, I don't want PSI. I want atmosphere. So divide by 14.7. I do not want liters. I want mLs. Moles are good. My R value is the same. This time we're looking for temperature. So we got to go, we're going to find it in Kelvin. We're going to have to convert it to Celsius. And then the final answer is Fahrenheit. Right? All right, let's plug this guy in. So P is 30 divided by 14.7. We're going to multiply that by the volume, which is 2,500. And that is equal to the number of moles, which is 4, times our R value, 82.1, times Kelvin. So I'm going to put a big K here so we remember it's Kelvin. So what is our Kelvin temperature? So we're going to divide both sides by 4 times 82.1. So let's do 30 divided by 14.7 times 2,500 divided by 4 divided by 82.1, and I get a K value of 15.5. Let me double check. Is that what you got? 15.5. All right, so let's go ahead and add in or subtract 273, right? Now give us Celsius. So we are at negative 257.5, and then convert to Fahrenheit. Let's see, 257.5 C. So I got 4, 95.5. So that's hot. That's super hot. Not too bad. Just remember your units. Units are very important. Everyone knows how to convert into atmosphere. You got 760 torr, 1,034 centimeters of water, 7.4 pounds per square inch, and 101 kilopascals. All right, let's go ahead and log on to the assignment and get you guys started and give you credit for today.